Okay, so welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome Katie Grasher to give the talk this week. So Katie got her PhD from University of Massachusetts. Daniela Calzetti was her advisor, and that was in 2018. She then moved to Australia as a postdoc, including as a DECRA postdoctoral fellow there. It's a great postdoc position. In fact, it supports also PhD students. At this point, Katie is supervising 3 PhD students and has been working in Australia there. We'll hear about her work on the abundance scale of H2 regions, but she's more generally worked on star formation and star clusters and a range of topics in star formation and extragalactic science. So welcome, Katie.
Great. Thank you. Okay. I'm aiming for this to be quite casual. We'll see what the camera decides if plans giving the talk. So if you have questions, feel free to ask. I have, aimed for that 30 minutes plus 30 minutes discussion, but how that 30 minutes is interdispersed, right? Yeah, that's fine. So hopefully by the end of today, all of you will agree that cosmic chemical evolution underpins nearly, so my mouse will out, right? Underpins nearly every interpretation we have of all galaxies across cosmic time. But it's difficult and complicated, and there's a lot of nuances, and we get it quite incorrect in many ways. And that's because in the end, we don't have a robust link to connect stellar abundances of what we see in stars, which are good tracers of metallicity, to the abundances we measure from emission lines that we use to interpret galaxies across the universe. So we're going to talk a little bit about, how we use emission lines as tracers of galaxy chemical evolution, and then how we use diagnostics, that's how we need to measure the metallicity within the interstellar medium. And then with that, we're going to jump to 2 surveys. One is the Typhoon Integral Field Spectroscopy Survey, which is how we link our interstellar medium enrichment to the more broader conditions of the ISM. And then a new program that we have, which I hopefully spend most of the time on, which is taken from the WIPES IFU, an integral field unit, but as well as the UVES high-resolution S-shell spectrograph on the VLT of individual result H2 regions. And the whole idea of that is to go, can we go and separate our temperature and depletion and chemical abundances to help us interpret galaxies? So I'm going to talk a lot about stars. I'll talk a lot about gas, but it's really that combined story of stars and their ionized medium that tells us about how star formation evolves over cosmic time. And the practical reason about, in my opinion, of why we care so much about stars is nearly all the light we see at all wavelengths comes from stellar or stellar process light. So if you want to understand anything in the universe, as it turns out, what lies at the bottom of that, what gave you that photon? It was a star. So we're going to take this really nice H2 region, right? We have young stars, and now you're talking about young stars, typically talking OB stars. They emit all their copious amounts of ionizing radiation. This goes and it hits the ionized the surrounding gas, and that's what you see as your H2 region. And these emission lines that we get from this ionized gas cloud, they're very, very bright. I mean, we can just look at it by eye. There's many, many more photons coming from the gas as opposed to the stars. And so if you want to understand anything about the stars, what we're actually going to look at is studying the gas to try to infer this property. So we want to make sure we get that right. And the reason why H2 regions, so ionized gas and the emission lines work so well is because chemical evolution is directly shaped by the star formation within galaxies. And emission lines are just really good tracers of that. And so we start off with this pristine gas cloud, early universe, hydrogen, helium, made the first stars, population 3. And then over time, those stars process heavy elements, which then those stars die, they're put back into their interstellar medium, and that process goes on and on and on again. And so we tend to think of stars as good tracers of galactic archaeology, because their metal content increases, but the gas also does it as well. And so your gas is really also can be in turn a really good tracer for your past star formation history of a galaxy. But this nice simple picture that I made, as you can imagine, the universe doesn't actually work that way. here's a little simulation coming from TNG 50. And you can see it's not just, you have a star, it makes the H2 region, which is slightly more enhanced the metal content and makes that, because your metal enhancement is also have very complicated factors of things that decrease your metallicity over time. And these can be, inflows of gas, they can be merging galaxies, they can be outflows. So when we look at this galaxy and we say, oh, what's the metallicity of this galaxy? That's actually a different answer, because while a star particle or star is a star, there's no such thing as, what's that gas partial versus that gas partial. And so your spatial distribution of what you see in metal content really represents just a snapshot in time of this production history in that balancing of the metals and mixing. And so then when we say, what's the metallicity of a galaxy? We get these images, you probably have all read these papers of, here's a galaxy from JWST and it has a metallicity of, at, redshift of this, 16.2. I don't actually know what we're quite up to yet. What's its metallicity? It's really more complicated than that. Because the metallicity of the galaxy is not as easy to define as we make it out to be. We just happen to be observing it right now within the gas. And it's actually an open question about how significant actual abundance fluctuations within a galaxy can be. Because you saw, if we would go back to that image and we would watch the formation of that galaxy, it would start off as the itty bitty little galaxy and it grows inside out formation. And so we're naturally going to have radial gradients and azimuthal gradients and hot pockets. And so we have to take this into account when we say our galaxy has a metallicity of this. So then what we're going to do is we're like, okay, well, if that's true, then what we're just going to take our young massive stars and we're going to take its gas phase physics, and we're thus to understand them on an individual scale. And then we're going to use that to try to help us inform then how galaxies assemble their mass and structure over time. Primarily, we're going to do that with emission lines. And if we're not quite familiar with what we refer to as gas phase metallicity, this is just, we're using our nebula emission lines. This is mostly from oxygen. We like oxygen so much because, it's the most abundant metal in the universe, very, very bright, comes in the optical. And the assumption that something that's really important to remember is that we use calibrations to get this. So we actually can't measure gas, the metallicity within the gas. We measure calibrations. And the way this happens is we'll go and we'll get an H2 region and we'll hit it with a spectrum. And we'll talk about these data in a couple slides. So we just have flux versus wavelength. And you can see we have about 10 emission lines that we were able to measure. Everything from different oxygen transitions, hydrogen, and helium, sulfur, and nitrogen. And so what we go is we make photoionization models. We'll put in a star cluster. We go and we run rate of transfer, and we say, okay, if I would have had this much O2 and this much O3 and this much H beta, and I take the ratio, this is what we call the R23 diagnostic, very common for metallicity diagnostic. This will then give us with the assumptions that went into our model, we will then say, oh, this gas cloud would have had this metallicity. It's hard because these blue lines, if you're familiar all with optical data, it's very hard to build instruments to go down much below 4,000 angstroms. Has a fairly wide wavelength range, about 1,500 angstroms. So dust correction is really important because your dust really eats your blue lines as opposed to your redder lines. So we can avoid these complications by going to the red part of the spectrum, and we can just use, H alpha, nitrogen, and our S2. They're essentially right next to each other, so you don't have to dust correct at all because their relative strengths are all the same, and they're in the red. We can do that. The problem with this is sometimes metallicity calibrations can be double peaked, and so you have to know already, so you can have a ratio which can be indicative of low metallicity, but the exact same ratio can also be high metallicity, so you can have double peaked, and those are kind of issues. One last one, which is my personal favorite, is N2O2, which is just the ratio of these really red lines to these really blue lines. And they're really nice. you're gonna, take broad wavelength range. Dust correction, really, really important. We always have to make sure dust isn't driving our result. But the nice thing about this ratio is within our models, it does appear that it's relatively insensitive to pressure within the interstellar medium. You can turn the pressure up or down. It doesn't change the ratios very much. You can turn your ionization, basically how hard the stars are ionizing their gas. Turn that up or down, doesn't change the ratio very much either. So again, these are what we call strong line calibrations. We're just taking really bright lines and we're making assumptions to turn them into a metal content. There's also what you probably have heard is called direct or electron temperature metallicities. And these are based on using collisionally excited metal lines that depend on the electron temperature. And so the way they work is we use things like nitrogen 2, this brings you back to, or this oxygen 3 line of where this transition, sorry, I'm gonna use my mouse, where this transition from, 57, 55 in nitrogen 2 to these blue lines, or going from the green to the yellow, that's purely determined by how hot your gas is. Not by your density, just by how hot the gas is. So then we can take our spectrum, right? And then we can look at the ratio of, this green line to this yellow line, or this red line to that blue line. And we just take our emissivity calculations and we can turn the brightness of these into actually how many oxygen or nitrogen atoms exist. And this allows us to go from the number of atoms to a metallicity, which is a better estimate. Now, if we look at this spectrum, and I'm going to quickly go and plot on the spectrum that we saw on the slide before, you're going to notice that these weak lines that are temperature dependent, we do not see in typical. So this is an extragalactic H2 region. This is within the LMC, and we've observed it for like 2 solid days, which is hence why we can see it. It's really hard to see them. So we don't tend to have these direct measurements of how hot the gas is. And because they're 100 times weaker, we have to usually rely on these strong line diagnostics. Which then, makes that issue of you need to be able to predict. So if we're just using emission lines to predict our metallicity, we should know how to predict our emission lines and metallicity, right? Everyone's uncertain. So here we have the exact X and Y axes don't matter. It's just transitions of sulfur to oxygen. But what does matter is, the black is showing manga data and the gray points. So whole galaxies, black and red are galaxies, and the gray are showing individual H2 regions. And we're going to go run our state-of-the-art calibrations based on what we believe the ionizing star sources are of these galaxies. And output, we get this grid of where we have galaxies increasing in metallicity to the right and increasing ionization parameter, which is just basically your ionizing photon flux over the hydrogen number density going from the floor to the ceiling. And you're going to notice is those two don't overlap very well. So we have put into our models of what we think our bright emissions lines should look like, and we're missing it. There's something wrong.
Is dust yet in there or not? So
Theory, they have been corrected for dust, ideally. Dust tends to, dust would, I think, makes it move this way, which wouldn't necessarily fix. It would help the ionization parameter a little bit, but it's not necessarily going to help metallicity. And one of the issues that I think, and hopefully you will agree with me by the end of this talk, is that a lot of times there's just a mismatch between what we put in our knowledge of stars and what we actually observe within the interstellar medium. And the reason underlying for this is what's called the Ono problem. You've ever heard of seen the Ono plot? So this is just the plot of nitrogen to oxygen as a function of metallicity in units of 12 plus log over H. And one of the issues is all of our things are pegged to what we see in the sun. And the sun lives in this blue circle right here. But an issue is nitrogen is very complicatedly made because it has both primary and secondary production mechanisms. So primary is this horizontal line. Nitrogen and oxygen are made in lockstep. Doesn't depend on the metallicity of the star. You're going to always make the same type, the same number of nitrogen and oxygen. But then we also get secondary productions of nitrogen. For every oxygen atom that's made, we get significantly more nitrogen. And so we live along this curve. And so we go and we make metallicity calibrations, we will assume that life lives and slides along this red curve. But you can go, but it's very complicated because the stars that make your primary production are very different from the stars that make your secondary in terms of mass, in terms of metallicity, in terms of time scale, because supernovae type 2 are instantaneous producers of metal enrichment, as opposed to, your AGB stars, which take forever. You can also have inflows and outflows and mixing. And then when you go outside and just take 4 random, plots of what people feel their observations of N to O metallicity are, you can get almost anything you want. So we don't actually live along this curve. And this is just for nitrogen. And you have all the other elements too.
So just remind me, the secondaries from AGB stars is
Yes.
Okay. So you get nitrogen but no oxygen.
Yes. We get the same problem with carbon as well.
Mm-hmm.
That's especially problematic like this. And so because of this, our metallicity calibrators can just be quite messy. So here we have an example of, a given emission line ratio of 3 different ones, oxygen to nitrogen, the O32, as a function of metallicity. And, for if we just, pick a value of 8, we could have, there can be a whole dex difference of what you would expect observationally, those emission line ratios. And so then when someone says, oh, we have this galaxy that we've gotten this, it's always, what calibration did you use? And then you go and you tend to use this like 10 and you give them all because we don't know what the answer is. But this is for high redshift of where, we've gotten all of our light and we basically condensed it to like 1 value. And it's probably going to work better at low redshift, right? Yeah, okay, I like this face here. It's also a mess at low redshift too. So here we're showing nitrogen, oxygen on our y-axis, and we're going to do this with an oxygen measurement, nitrogen, oxygen versus a nitrogen and sulfur. These are the same ones that I showed you earlier, and you can see it's a mess. It doesn't work well. If you don't like the answer, just change to a different calibrator, and you get something by a dex difference. So it's kind of how the sausage is made. And so our interpretation of really all galaxies, it's important at low redshift because, the spread does increase at the low redshift, low metallicity. The spread does increase more at the low metallicity, which matters more for high metallicity. And so what we would like to do is to understand, why is that happening? What can we do to make it better? And what drives these observed discrepancies? Because we don't know. And so the question that I would like to ask is, well, what is the actual chemical composition of a galaxy? And do H2 regions actually have the same abundances as their stars? We make these assumptions, but is that actually true? And I'm going to argue that we don't know the answer to any of these is because we don't have independent measurements of the true total abundances in which to actually compare our diagnostics to. And so what we're going to do is we go out and we get some nice integral field spectroscopy. And so we start off with this beautiful 3-color image taken from Muse. And the beauty of 3D data is that it gives you, an image. So it's, you have X, Y, and Z. So you can have an image at every single wavelength. Or at every single pixel, you can have a wavelength. And so there's a wealth of data you can get. You probably already started to learn some of these emission lines, from the spectra I've showed you. And so there's a wealth of information you can go and learn about the interstellar medium that you simply can't get from just images or single slit spectra alone. And so our first attempt to go and try to understand this was we went and we did what's called the Typhoon Survey, which I call the poor woman's eye of view. And so we got 50 galaxies taken with the DuPont telescope at Las Campanas Observatory. And IFUs are expensive. You can imagine these 3D nature things, that's very expensive. It takes a lot of photons. And so what we decided to do was to be smart about it. And we took a slit that's, 18 arc seconds long, 1.65 arc seconds wide. We observed it 500 seconds. We moved it over by exactly 1.65 arc seconds. And we did that a couple hundred times. And you build up a whole image of the galaxy. And the beautiful thing about this, this single slit spectrum, very broad wavelength range. And we have resolution that's about 50 parsecs on average for a given spaxel, which is about the size of an H2 region. So we're not quite resolving it. But the thing that we have that other facilities don't have is, because if you know the size of Muse, which is a very famous one, Muse would be like about as big as one of these individual H2 regions. So we can go from the inside all the way to the far outskirts of the galaxy, which is something you just cannot do without infinite time on an instrument like Muse. And so here we have an example of, this is 12 galaxies, 15, if I've done my math right, of just showing you metallicity gradients, just to show you just how different metallicity gradients can get. So oxygen as a function of radius on the bottom, they're being color-coded right now by the brightness of the regions. And something that you notice is, in general, they all have a negative gradient, right? This is indicative inside-out growth. Galaxies that are very, very metal-rich tend to be more massive. That's just because they've had a really long time to build up their metallicity, as opposed to more of these wimpy things, which kind of have constant star formation, maybe lots of mixing. There's actually a lot of active work going to try to understand why things have the shapes they are. Like, the fact that this one's flat and then decreases, is that meaningful? These are all indicative of different types of star formation histories. So something that we did was we went, and now we're going to take this and we're going to subtract off the metallicity gradient. Because we don't actually care that this galaxy's steep, this one's shallow, this one has a lot of metal content, that one doesn't. So we're going to basically subtract out this average black line, and we're going to get the relative metallicity variations, so the delta over H, between every single H2 region. And this is being plotted as a function of ionization parameter. And if we remember our stellar classes, but maybe some of us haven't taken our stellar classes yet. When you have when a star has very low metal content, it tends to be very, very hot, very, very bright, very hot. And then once you start to add metals, the metals essentially act as a coolant. Okay, so your ionization tends to go down, your temperature tends to go down because it cools more efficiently. So which means that, when we get to higher ionizing H2 regions, we should have a decrease in our metal content because the ISM acts like a coolant with more metals. And you see that we tend to not do this. We tend to have instead an increase of where we have more ionizing H2 regions tend to also be associated with more metal-rich ISM conditions as well.
But is that just calibration then? Because a single calibration was with a single ionization, or did you vary the?
So
when you did the galaxy fit?
So what we have done is, we've done the same thing of where we hit this with about, 10 metallicity indicators. But the problem is sometimes, a lot of times there's a degeneracy between metallicity and ionization parameter here. But we have removed that.
Okay, we can come back to it. Yeah.
So what we think it's saying is it's essentially just, the fact that we tend to have high. So what I'm showing you here is now basically collapsing it all into one plot. So we have although I did swap the axes, apologize for that. We do have our log bar ionization parameter as a function of metallicity. So we're using N2O2. And now they're being color-coded by their average metallicity offsets within each galaxy. And so I think what it's just suggesting is that there's very localized metal enrichment. So like, we just happen to be looking, so it was a fairly shallow survey. And so we just happen to be looking at the burst of the most recent star formation history, where you have the coexistence of your intense star formation burst. And it's quite young, so your metals have yet to disperse, right? So then you produced, both your hotter stars, your hotter younger stars. So it boosted your U. And that also in turn makes your compact enriched pockets where you have both an increase of both. So which tells us that our metallicity and our ionization parameters don't necessarily co-vary. They aren't the same locally, which when we put them in our models, we always assume that they slide together. So this is already an issue. But they don't directly cause each other. Exactly digging, we haven't published this yet. Exactly digging to the bottom of this, we have still yet to quite figure out how to do, because I'm not quite convinced yet. And I think a lot of the problem is in our models, especially going to our stellar winds, and it's geometry. It's assuming the geometry is what's going to go and solve this problem. So then, if the issue is we can't quite figure out, so if the issue is we can't quite figure out how to disentangle ionization parameter from metallicity, and with star formation, your star formation history.
Do that later, yeah. Sorry.
Okay, the ground truth is, okay, let's not do this at global systems. Let's go down to an individual star and try to figure out how life works there. And so the goal is to create ground truth diagnostics based on reality of where everything. This is an individual O star within the LMC or SMC. And we're going to go and get our nice IFU observations of it. So we'll be able to tell you temperature, the density, the pressure, ionization, metallicity, abundances, and the stellar parameters at, less than a parsec scale, a tenth of a parsec across this region of this star that's probably less than 1 million years old. And then the idea is, well, we know the star completely accurate because we hit it with, an R40,000 shell spectrograph coming from UPES. And so we can tell you all the stellar abundances, and this gives us our true baseline. And then we can go and get our nebular information, and we have the full spectral coverage, so we know temperature, density, we know our jumps, we have multiple iron lines within the interstellar medium, and this is how we can look at the depletion effects, because things like iron deplete very heavily into the gas, and we also can look at our nebular continuum, which gives us our internal reddening, and we do this within a full parameter space sampling, because we fed in the star perfectly, we have fed in the gas perfectly. And then with that, we can finally start to understand what drives our uncertainties. We can understand why they differ, and if they differ, why. And then you get this, and you forward model it to essentially what would this be if this was a galaxy? And then where would we start to deviate? You do that across, 50 different H2 regions, and you can start to say, oh, the ones with low pressure tended to break the most, the ones that were located in very dusty regions. Okay, so I put in this program last year, 100 nights, divided between UBES on the VLT and Siding Spring Observatories facilities, which are in Australia, to get H2 regions. The program got up, which was kind of surprising. We're aiming for about 50 H2 regions. We hit them anywhere between 4 to 48 hours. Exactly why we have that wide spread, you can ask me about that later. But here's an example of one of our H2 regions. Here's an example of the central star that's powering it. And this slide always takes a while to load, and I don't really know why. And that beauty is, because now we can feed our star into mappings where our grid of, our density and temperature we put in from the nebula, and we can get both our mappings emission lines. And we also have our nebula continuum. And if you don't, so we actually have yet to feed in the exact star. Right now, we're just feeding in the theoretical star that we believe matches the H2 region best because, as it turns out, it's really complicated putting these stellar parameters into photoionization models. But I'm showing you here an example of one of our red data come in, the data in the red and the black with our model. And you can see that it matters, so we've taken a generic star that has third the metal content of the sun. So we've taken the sun scaled down. And you can see that, sometimes it does really good and sometimes, it doesn't. Here we go, Mappings, our photoionization model says there should be a ton of magnesium, and there isn't. We tend to underestimate iron a bit. Sorry, the observations don't show as much iron as our models do, and some of our neon and oxygen lines. So there's a lot of work to be done, and that shows this thing of, we're not feeding in the same, so we already know that the answer might not be quite correct.
Is depletion a parameter?
Oh, that's a good question. Let's go find out. Yeah. The depletion we have is probably the answer to this. Yes, the depletion is maybe not for magnesium. The magnesium one's a bit surprising. But for the iron ones, the depletion, that's one of the first projects we want to look at. Okay, so if we go back to our typhoon, where we have the whole optical range and we found we only have about 10 lines that we can look at. And we go and we plot in our new data. This is what it looks like on the top, way more than 10 lines. And I'm actually just going to go and plot a little 150-ish angstrom region near the red. I mean, I'm not personally used to seeing, chlorine and chromium and, neon 2 in my spectra. Like, it's kind of surprising that we're getting all these things. But it's really exciting. And I'm going to end with, we're going to show us some early results, some science results. And so I had an honor student, an undergrad student, who's now a PhD student at the CFA in Harvard, who went and decided to look at the correlation between H2 region properties and the different ionization zones and temperatures of different species of metals. And so here we have one of our H2 regions. We can see the density, so these are selected to be single stars, spherical, so they're really easy to model. Okay, so we have density, metallicity, ionization parameter, and temperature. And so we actually have the ability to look at the temperature zones for all these different species. But for her honors projects, she only looked at O2 and O3 because these are the most common diagnostics that we tend to use. And so here's the map of, in our low ionization zone, which uses just singly ionized oxygen, as opposed to on the right, we have our high ionization zone, which uses our O3. And remember, this is using a direct metallicity indicator. So we're just taking our flux that we're seeing of our lines because they are sensitive. These really weak auroral lines are sensitive to the temperature. And we just have to multiply these by emissivities of the lines, and this will allow us to get approximately the number of singly ionized oxygen atoms and doubly ionized oxygen atoms. Unless you're in a really high excitation blob of a galaxy or an AGN, usually most of your gas just lies in the first 2 low ionization zones. And then what we're going to do is we're going to take the difference. So essentially going to take map 2, the first map, we're going to divide out by the second map. And we can see this temperature variation that's within a single region, has variations of, plus or minus over 5,000. And then with that, we can look at the number of oxygen, essentially atoms, singly ionized oxygen atoms within our gas as a function of our temperature variation. And we did this for 3 H2 regions. We see there's a very strong trend. So the temperature variation you see very much, sorry.
It's OH plus.
Yes, this is OH plus. We can also do it for OH plus plus.
Oh.
Okay, so when we're in our low ionization zone, so just OH plus, there's a very strong trend between the number of singly ionized oxygen atoms you get as a function of the temperature variation between these zones. But when you plot it within your higher ionization zone, so O++, it's completely flat. How you doing?
Think about it.
Right? Which then becomes that surprising thing because, well, typically, right, what did I show you here? You know, typically to estimate our metallicity, we take our lower ionization zone and add it to our higher one. And when one has a strong temperature dependency to it, that's always going to make a temperature dependency fall into your metallicity calibration. For instance, so this is showing a difference in a direct, so the true metallicity versus a strong line calibration. And you see, we always, maybe it's not so bad for R23, but since you have that strong within our low ionization zone, only the low ionization zone, since we had that strong trend, it just bleeds through your temperature variations. And then this could be one of the, and so this disagreement that we see of one dex between direct and strong emission line diagnostics. One of them could be the discrepancy correlates very strongly with that temperature fluctuations, which is present in some zones, but not all the zones, for this specific H2 region. And, you know, maybe we should have seen this coming in, because if we just looked at, say, this density diagram, while there was chosen to be a single star in a spherical cal, you can already see there is density on structures. Okay, and with that, this is my conclusion slide. Now to say, you know, chemical abundances, right, they underpin every interpretation we have of galaxy evolution, but we rarely have independent measurements of which to compare our true total abundances against to compare nebular diagnostics. And so what we're doing is really trying to separate how temperature structure, how that impacts us from depletion, to compare our stellar and nebular diagnostics and to make dust sensitive diagnostics as well. And so, and the way we do this is, you know, you have to take your stellar abundances, which gives you your total composition answer. No, then we have to take our nebula spectra, which gives us our gas composition, because that's actually what we measure from emission lines. We have to get a handle of the dust to figure out how much depletion matters. And then, but we also need to go and use our continuum jumps, which we're not talking about in our war lines, to give us a temperature structure. And this is where we think this temperature structure specifically is one of these drivers in some of the uncertainties in the diagnostics we see. And with that, I will, thank you.
Thank you very much. So, for Katie. So maybe Mary Grace can help me there if there are questions in Virginia side, or online raise your hand, or here raise your hands. Maybe we can start with the single star H2 regions. Just talked about it.
Yeah.
How many H2 regions then do you have this kind of data? This plot is just one H2 region.
Yes, this is just a single one. Yeah. Oh, no, sorry, this is three. The colors represent three different.
So how many do you have? And then can you correlate stellar temperature with ionization parameter, for example?
So in the end, we're hoping to get around 50. As of right now, we only have 6 because we just started observing last year. The LMC and SMC only come up the second half of the year. We're hoping to get about 50. And
but
yes.
But do you notice that, what are your stars here? These three, are they all O stars? Or?
So the problem is they're mostly O stars and a couple B stars. So looking at, say, temperatures between like the actual star and things might be difficult because, you know, you need the emission lines. You need your emission lines. You'll really be biasing ourselves towards a certain star.
Yeah, but do you think you notice that the earlier type O star has a higher ionization parameter? Is that sort of popping out of the data when you infer from the nebula diagnostics?
With 6 stars, no, I haven't looked into that, but that is something I think that'd be
just to check, you know.
Yeah, it would be the most important thing to do with, you know, your slightly bit. Yeah, yes.
Mm-hmm. And then, of course, one could go to depletion measures. I mean, it's this question of whether with the abundance of dust in the H2 regions that's been around for a long time.
Yeah.
I don't know if you have any thoughts on what the evidence for depletion is in the nebula gas.
So I was at a conference a couple weeks ago, in Greece, the conference that we were at, and there was a really interesting talk. Is because usually what happens, our knowledge of dust within the Milky Way is, if you have, say, just put an iron atom into the universe, and it has like, a 99% chance of just going to get sucked up into a piece of dust. And this is why we never see iron within the interstellar medium, which is why we can't measure iron, is because it's all on dust. And there are some magnesium and silicon are also heavily locked into dust. So, the question of why we didn't see magnesium in that one source could just be because there's a lot of dust. But it's interesting is because when you go to lower metallicity systems, I saw a talk a couple weeks ago about like the importance of iron became deweighted, and there was more of like your silicon or your carbon would start to get depleted, which that gets very complicated very fast. And I don't know how to deal with that.
So you're going to measure from this data, you're going to measure depletion.
We're going to measure it. And so the way that we are going to measure our iron depletion is we essentially just start to look at iron colors, and we just essentially look at, what's iron 1 to iron 2 to iron 3 to iron 4. And then that will give us, because we should know what those colors are based on quantum mechanics, and having an understanding that would tell us how much is locked into dust. And because we also have so many transitions available for other elements, in theory, that can also give us an understanding to see, is silicon also locked into dust? Because things like oxygen should almost never be depleted.
Right.
And so we shouldn't see our oxygen colors changing in the same way. Shouldn't.
Well, but there is some oxygen in the silicates, and then I'm wondering if the dust is it higher temperature H2 regions are less depleted, I don't know, grain destruction or something. That you could check as well. And then there's a question of sulfur depleted.
Don't even get into the sulfur data. Yes.
Yeah. Anyway, Maya, yes.
I have a question about one of your figures from a couple of slides ago.
Yep.
Yes.
Yes. Okay. Sorry, I realized I went over this really fast.
No. Yeah. It was very interesting. So here you said you have 3 stars, and I see that 2 of them are in the SMC and 1 of them is in the LMC.
Yes.
Yes. And I was curious about the panel on the right, because we have one type of relationship for the SMC stars and a very different one for the LMC one. I was wondering if it was clear why.
Oh, wondering why? Like what I think of this? On at first order, I would say, so the LMC is about half solar metallicity, and the SMC is, right? If you remember from the beginning of my talk, you can't say a galaxy has 1 metallicity. Hopefully you're all paying attention. And the SMC is about a third. And so the fact that, orange star is so different, right? Probably could just be a indicator of the overall metallicity indicator, could be a different dust depletion, or different abundances. It's probably one of those. We did not investigate that in this specific paper. We now have, we have now doubled the sample. And so, and I suppose, right, we could go and put them on the plot again, and see, like, is this an oddball out?
Yeah.
Right? Or does, the SMC and LMC tend to show same things, same trends? Yeah.
Well, just to comment, we have this LVM data in S284, or it's about half solar. So in our galaxy, we can do some tests like this. Yeah, Doha.
Maybe it's a bit far, but if you can go to page 40 or somewhere around there.
Can the camera pan out and see the room? Actually, is there a pan mode? Or...
Do you remember what was on this?
There were like 15 that you were saying the geometry can be the solution. I was wondering, what do you mean by that, like geometry?
So the way photoionization modeling works is we get our ionizing source, we put it in, and then you put on a slab slab of gas usually, and then you just watched, you know, what happens to the photons that went through this infinite slab of gas as you on the observer. But the issue with that is that's not how the universe works. And doing this very much simplified geometry doesn't actually work well. So one of the reasons of why for some of our H2 regions, you know, we've literally stuck days watching on them so we can observe down to, you know, every single transition of iron is because we're actually using 3D photoionization modeling for our nebula. And so, you know, we literally put in the structure of our nebula. You know, we don't assume, you know, infinite flat slab. And we put it into to get out, you know, a nebula that, you know, looks quite good. And it takes 3D modeling and it takes like, you know, 62 million hours to do this, which is, you know, I mean, that's a slight exaggeration, but it's not far off. And the emission lines you actually get from your proper 3D photoionization. So take into account the geometry and the fact that geometry is quite complicated and it's not just an infinite flat slab, you get completely different measurements from.
Also related to that, this evidence for stellar wind bubbles inside H2 regions. So in your previous one, the density was peaked centrally, but do you have evidence for, I don't know, shell-like H2 regions which have a wind bubble inside? And does that, if that was common, would that make a systematic impact if it was unresolved?
I don't know the answer. I mean, this is a good question and a good suggestion. I actually don't know the answer to that.
The ones you have 6, I think you said.
Yes,
individual.
Yeah.
Are any of them shell-like, or do they have?
We have no, but we have some that are being put on the queue. And why are you more interested in the shell ones?
Well, do H2 regions always have a wind bubble? And if not, why not? And you know, of course, the stellar wind properties vary with stellar properties, but stellar wind should impact. You know, its round pressure sweeps up the H2 region and so on.
Yeah.
You know,
right? Because I suppose. Right, because I think you would get right, because there should be a difference in, right, so if you had your stellar wind bubble as opposed to your radiation bubble, right, you would see that in the emission line somehow, you know, whether or not it would be, I haven't overly looked for it, for the signatures of this, but it is something to think about. It is something to consider because that would be a cute result.
Yeah, if you have a nice system like that, and
no, because you know, let me tell you, I can't tell you many papers that have shown things like this.
Yeah, maybe you have the data to do it. Please, Patrick.
Can you go back to the plot you were just showing a second ago with the I don't know, 20 or so?
Yeah.
So oh yes, this one. Yes. So you mentioned, I think, if I remember that, this could be biased towards more recent star formation events.
Yes.
Which have less time to disperse the metals. Yes. Is that something that you could see as a trend even within these that we do have? Or like, is that something that we could actually confirm just based on, you know, the tip of the iceberg that we do have? Or
so, you know, one of the reasons, so basically I think the answer is it's just, you know, my number one here, you know, the most massive stars are still alive. They just formed, thus they've enriched it. And it's just like an age effect. The thing so the points here are being color coded by H alpha luminosity, which is, you know, a fairly okay-ish way to describe the age of an H2 region. Because, you know, as soon as your H2 region is you know, older than 10 million years, you know, it dies. It's like instantaneous die. And if you look at this, there's really no correlation between color in any galaxy, color of the points, and anywhere in any of the plots. Like it's
Yeah, I agree.
kind of just scattered points, like, yeah, I mean, this one we have all of our bright H2 regions are, at the bottom of the plot. This one, I mean, it's hard to tell looking at, we don't do science by eye, but this one
Yeah,
on top of the plot.
right.
This one they're all middle. This one actually,
Yeah, I was gonna ask about that one actually.
that one, I mean, so this one actually probably the color bar just needs to be improved.
Yeah, yeah.
But really had no bright ones.
Huh.
And so I would have thought that would have been true. And then it could have just been, bigger is better and bigger always wins. So it could just be, you get more high mass stars, so more ionizing photons, so more U.
Mhm.
If you had a bigger GMC,
Mhm.
right? So could this be, those are the big bullies of, the neighborhood. And so those gave harder ionizing photons because you had more size. So it's a size or a mass problem. But the issue with that is, and the beauty of these galaxies is because, things exist.
Right.
So we actually have ALMA resolution of about the same resolution we had.
Mhm.
And you can see, so here we have ionizing photons, ionizing parameters. This is not the same thing as capital Q, functionality, color coded by, if you would multiply log of ICO, right, by an alpha parameter, that would give you the mass of a CO cloud. I just haven't done that because, I don't know what alpha to pick, right? And as you can see, that's quite a scatter plot. But maybe there's a trend for, as it turns out, smaller clouds to have a higher ionization parameter. Right, which could tell you that, maybe your ionizing photons are more quickly absorbed or essentially just trapped within more denser clouds.
Mhm.
So thus that would give you a smaller ionizing region, which would correspond to a smaller strontium radius.
Or it could be the smaller GMCs are in the outer galaxy, a lower metallicity.
But it was normalized out, right?
We did normalize that out, the
Oh.
metallicity.
Oh, the gradient you already
Yeah,
written out.
yeah.
Okay.
Right, it could also be, right, those regions are more embedded, they're dustier,
Mhm.
and or they're older, and thus you have that lower observed log view.
Huh.
So any other questions, especially online, raise your hands, or in Virginia there, let me know. While you're talking about the FANGS galaxies, I noticed a range of different gradients and metallicities.
Yes.
Does that correlate with anything? Like why are some galaxies flat and others have quite a strong? Has that been looked at?
This is it's still a quite active debate of exactly how it's essentially telling us the information about the star formation history of a galaxy. And things like this little peak here is probably due to being driven by a bar. That tells us there's probably a bar thing.
More the global gradients that I'm seeing. Yeah, some are very flat and some are. So just if that correlates with anything.
This is just so in general, the gradient corresponds with inside-out growth. And inside-out growth is something that's very, very common in the way that galaxies are formed, and especially in the local universe. When you go to higher redshift, more flatter, or even sometimes backwards gradients tend to be more common. Exactly why, NGC 2442 has such a flat gradient. I don't actually know the answer to that. It's also a fairly small galaxy.
Mm-hmm. Okay, just curious.
I don't have a good sense of how long the time scale is for that to change as you get, gas inflow and outflow.
It could also be an indicator of very efficient mixing
Mhm.
Yeah.
in this galaxy, right? So we have, essentially flattened out all the enrichment.
Winter, did you have a question?
Yeah, just a small one about, I was just curious why you guys chose to observe for between 4 and 48 hours.
So this observation is 3,000 seconds. I mean, not in one, right? It's a series of like 1,000 seconds stacked together. This one is 3,000, which is, how's that? How long is that in seconds? boy, you know, someone.
3,000. No.
I meant hour.
I know, I'm kidding.
1 hour.
Yeah, okay, so it's not very long and we already can see some really nice lines. We're not quite deep enough yet, so I mean, we need to go like, but diminishing returns, right? If you want to go and if we want to say, you know, go and better get a signal to noise measurement, because someone could say, oh boy, I'm not sure that is lying. We want to get a better signal to noise measurement on that. You have to increase your observations by like 20. Right. And so, you know, and so which is fine if your observations are only 5 minutes, right? Because a factor of 20 is not that expensive. But if your observations are already, you know, quite expensive to get this. And so because of that, we don't make all of our observations have such high quality because there's simply not enough time in years to get this done. Because this is a program being done over 3 years because it's 100 nights, which is 100 dark nights, which is a lot of time. And so the ones that we will be planning to put through our 3D photoionization modeling. So, you know, we want perfection in every step of the way. Those are the ones that we just essentially integrate forever. Up to, you know, 48 hours, which is, you know, 5 nights or something like that. But those ones we only do those ones are our most ideal cases.
Can you flip back to the previous spectrum you showed, the nebula continuum?
Yes.
Can you remind me then so the processes that, what are the processes that set nebula continuum? Is it like 2 photon emission, or is it
the 2 photons?
And so do we learn? So there must be, is it sensitive to density quite strongly then? So do you things like this? Well, anyway,
don't know that. So we're using it as a good internal measurement of our dust, essentially.
oh, it's dust, is it dust continuum as well?
Yes. Yeah.
I guess you have stuff, I mean, there's reflection nebulae around as well, so it may be hard to separate exactly all the contributions, but I'm learning about it. I don't know anything about it. Anyway.
So the mapping side of this is very much being led by Ralph Sutherland. Because he's very good at that. He's one of the co-developers of mappings is at ANU, which is, you know, very, very good coincidence, who's very much enjoying these data because it's pushing mappings to become better too.
Very good. Okay, well, we're at the hour here. If there are no other burning questions, we will stop the main session here. So I'll stop the recording, but let's thank Katie again.